So I thought first, since there weren't a lot of people in this agenda from the financial industry, I wanted to talk a little bit, just quickly, about what we're doing at State Street, because it's somewhat new. So we started about a year ago a new division within State Street. And for those of you not familiar with the bank, this is a Boston-based bank that does mostly custody business, but has branched into a lot of other types of businesses that we kind of call the piping of markets. So this is facilitating trading and settlement and clearing. It's a lot of the things that people aren't aware of, but it puts us in the center of a lot of data. And we're part of a group that is called State Street Global Exchange, and I run a division called Portfolio Analytics and Valuation, where we are specifically taking the data from our clients, which are all the largest financial institutions in the world. So imagine everything from pension funds to asset managers to hedge funds. We actually have the data of their positions because as a custodian, and often we're asked to help do risk analysis. So we then take the tools that we are developing in the risk space and apply that to all this data. So that's basically what we do. And what I'd like to talk about today is just a quick overview, because I know there's not a lot of time in the session, of some of the types of things that we're focused on with respect to this data science question, which is becoming more and more important as people think about risk, particularly coming out of the financial crisis. All right, so first I thought that I'd discuss the motivation. So the motivation is to try to help our clients understand where they have stress in their portfolio. And we're defining stress specifically as these downside clustered events. So one of the things that I think we always knew this, but we relearned it in the last financial crisis, is the underlying correlation across asset classes tends to converge to 1 in these difficult situations, and as a consequence you end up getting these fat-tailed return distributions. And so that's what people are worried about. Now there's an old joke in finance that says, you know, how do you make $1 billion? And the answer is you start with 2 and you lose $1 billion. And so and that's really the big issue that these institutions are facing, because the people that are making the money are the ones that are selling the products, and not necessarily the people who own the assets. Now, all of us should be a little concerned about that, because all of us are asset owners. We're asset owners via our pension plans. We might have insurance policies, 401k plans, and often the risk is not managed in a way that optimizes the well-being of those people who own the assets, and we're trying to rebalance that. So trying to help people understand the stress and do that in a multi-asset class context. And this is really the challenge from a modeling perspective, because a lot of the research around in finance and in risk has been focused on equity portfolios. And equity portfolios have this nice property of having a much more symmetric distribution, meaning I have about the same probability density on the upside as I do on the downside. Now I have fatter tails than I like, so I have more extreme movement, but generally I can get diversification. But for most large financial institutions, that's not the type of portfolios that they're dealing with, and they have to respond to the stakeholders, which may be regulators, the people who actually own the assets, creditors in the case of levered funds or levered institutions. And the big data tools are really helping us solve this problem. Now, just as an overview, I thought I'd put this in here because a lot of people may not be familiar with the process, but when we go into a client to help them think about their financial portfolio risk, we start with actually risk governance, and that is, how do we think about, how does that institution define its risk appetite? And we do that in a quantitative way. So what's the strategy in terms of how much return do you need? And that's driven by the specifics of your institution. If you're a pension fund, you have to meet your liability obligations. If you're a hedge fund, you may be promising your investors some kind of return. So you have that target return, but subject to some tolerance that the institution's comfortable taking. And we like to define that probabilistically. So we say, look, only 2 or 3% of the time do we want to lose more than, say, 10% of the principal or 5%, depending on the objectives. So that's the start, because if you don't have a starting point, it's unclear how you should figure out how to manage that portfolio. From there, you want to characterize the portfolio risk in quantitative terms. And I'm going to talk a little more about the metrics that we like to use for that. And often, this may seem strange to people not in this industry. You would think that return and profiling the return should always be part of the discussion, but often it's not, mostly because the terms and conditions on the securities typically sit in a database that's separate from the information about the cash flows, which is a problem a lot of institutions are trying to resolve, but that sometimes can make it difficult to assign the return of a security to the risk of that security, although I think things are getting better there. From there, we estimate latent risk factors. So we look across traded securities, try to understand the underlying correlation structure, and then apply those factor sensitivities or factor loadings back into a simulation process that allows us to then figure out what is the probability distribution of returns. And then in the end, map that back to some kind of set of proxy factors, which might be macroeconomic indicators, so that a portfolio manager can understand the stress scenarios they should be worried about, or potentially even what are sometimes called style factors. There's a whole range of proxy factors you might use. These become interpretive means for understanding the portfolio. At each step of this process, we have to marry the data science with the statistics and the finance, and so that's what makes this problem quite interesting. So I'm not going to have time to go through this, but these slides will be available for you to refer to afterwards. But these are a lot of the questions that our clients are asking us. Just to highlight a couple of them, is my risk in the portfolio, is it aligned with my risk appetite? Meaning, am I taking the risks that I think I'm taking? And do I have the ability to manage those risks? So if I see big downside moves in the portfolio, can my resources absorb that? What's the return risk profile? And where are the specifics of that portfolio that I should be worried about? Now this is the typical, this is a stylized graph, but this is the output. So we're trying to look at a portfolio return distribution, and often we're calculating something that we call expected tail loss, but sometimes it's called expected shortfall or conditional value at risk. That's the average loss in this region where we see a lot of bad scenarios. And so that's really, a lot of the focus is trying to figure out how to estimate that piece of the tail. Now we use a latent factor approach, which relies on something like principal components, although it's a little more sophisticated than that, which allows us to account for different liquidity profiles of securities, weighting differently across different sectors and countries. That allows us to then extract a set of orthogonal latent factors, which can become the basis for some kind of a simulation. And then after the fact, we map them into a set of collinear factors, such as macroeconomic indicators, which have correlation among themselves, and that becomes a statistical process. Now this is an example of an output. So I calculate the portfolio value distribution vis-a-vis a simulation, and if I'm a bank, which is one type of client, I'm worried about the downside risk that's going to cause me to lose so much capital that the regulator is going to shut me down. And so that then the value distribution gets converted into a loss distribution. But you see, I still have this skewed picture that I got to be worried about, and each potential quantile on the distribution can be mapped back into, say, a rating, or a default probability. So that might be an example of an application for this type of modeling. Now the challenge is that our portfolios our clients' portfolios are huge. So, typically on a disaggregated basis, we're looking at millions of exposures. Even on an aggregated basis, we're talking about 100,000 exposures. And since many of these exposures exhibit skewed payoff distributions, we have to run lots of simulations to get any kind of accuracy or precision out in the tail. So that means we might be running, say, 1 million or 2 million iterations on 100,000 exposures with a couple of hundred data components. And I'm actually going to have one of my analysts talk a little bit about the data architecture, because that becomes a big problem in and of itself, just trying to process all that data and understand it and look at it in a multi-asset class context. And this is something we've only been able to do in the past couple of years. I mean, it used to be very siloed. So you would have somebody that would look just at equity, somebody would look just at fixed income, somebody would look just at private equity. Now we can put that all on the same playing field. And so this is an example. I guess I lose the animation, but anyway. So this is an example of a stylized example of how I get the different distributions. So this green one in the middle is close to a Gaussian distribution, which is characterized by small tails. And if I overlay, say, fixed income, which is this purple, I get a lower mean, and I've got this big tail region that I'm worried about. So holding just fixed income or having concentrated fixed income is never really a good portfolio strategy. So what I want to do is mix that with other types of assets, so I get a multi-asset class portfolio. That shifts the distribution back closer to what I might get, say, with just equities and hopefully smaller tails. So I mean, that's conceptually what we're trying to do, and we're doing that at the granular level of sub-portfolios and even exposures which might be accounting for a lot of the risk. So we think about risk contribution, which is a key conceptual component of this analysis, in terms of a systematic piece and a diversifiable piece. So the systematic piece can never be diversified away. This is the underlying core systematic risk that exists in the economy, and this is really what you should be getting paid for. Now, the game in portfolio management is constructing diversified portfolios such that you get paid as much as possible for that systematic risk. Now, since the markets aren't terribly efficient, contrary to what a lot of people thought a few decades ago, people get paid for even taking diversifiable risk. And so, those are sometimes loosely called arbitrage opportunities, at least in a risk sense, but that gives you, these models give you ability to essentially sort those different pieces out. Now, the risk metric that we focus on is this expected tail loss, although a number of clients also worry about volatility, and that's because it's considered a consistent risk measure. It is difficult to backtest, which is a problem with the measure itself, but it is something that provides a lot of guidance down to the exposure level, assuming that you can do enough simulations and you've got enough precision around the data components. Now, the constraints that we're worried about are, of course, the risk appetite, which I discussed, but we also have to worry about the fact that the nature of this expected tail loss measure requires us to run a lot, the more exposures I have, so if M is the number of exposures I have, the more iterations I need to run in order to collapse the confidence intervals to a level that I'm comfortable making decisions. And that's really the challenge you have in practice. Am I confident enough that the risk contribution estimate is reasonable to drive a particular decision? Because one of the big problems communicating to non-technical financial executives is why a model result changes just because of sampling error. I mean, it's the worst conversation that I have to have, because they just don't understand it. And so you want to try to make those confidence intervals as small as possible. And then the other challenge is time horizon. A lot of models are calibrated to short time horizons. We have many clients that are looking out 3 years, 5 years, 10 years, and then you have to start thinking about path dependency. You have to start thinking about a number of other issues that impact you over those longer time horizons. I'll skip just in interest in time. I've got a few reference slides here for you, but I wanted to show a little bit of data, because one of the things that we see in the data when we estimate our latent factors is this very pronounced volatility clustering. So if you look at these are the FTSE All-World Index, so this is a very common equity index, and you kind of group it across time. So this goes from 2008 to 2013. You can see these little pockets where you get a lot of spread in the data. Now, when we do our latent factor modeling, we want to condition on the volatility environment that we're in. And fortunately, we have a great instrument that's traded called the VIX. It's a volatility index that has a lot of liquidity, and the VIX provides a good estimate of future volatility, so it gives you a sense of what volatility regime you're in. So that allows you to improve the quality of your latent factor estimates by understanding that volatility clustering component. So that's an example of some of the techniques that you can use in this space. And you can see, in times of crisis, so this is pre-financial crisis going through May '09, the systematic component of, I've lost the legend here on the bottom, but that bottom curve, the orange, is actually systematic. When that jumps up, that's a reflection of all these correlations kind of bunching together. And again, using these forward-looking measures, we can at least get on top of that type of risk distribution. Now, this is an example of how we think about the factor model. So we estimate the sensitivities from observable data. It then gets converted into these sensitivities, which can be used to simulate that information. So with that, I think I'll talk about one more component, and that is interpreting the output. So once I run the simulation, and I say have my 1 million or 2 million iterations, and I then want to infer the types of scenarios, I have to go back and understand the relationship between those latent factors and the factors that I want to manage to. And it's this proxy factoring that requires either some kind of, we've looked at linear projections and also some nonlinear techniques that allow us to figure out a relationship between that orthogonal factor set and then the factor set that people can interpret. And this becomes an important step, even though it's not germane to the specific risk analysis. It's important for communicating to the people that make decisions. Okay, with that, I'm going to turn the time over to Nate, who's going to talk a little bit about the data architecture that we use, and then we'll finish up just showing you a couple of graphs of the data visualization output.
So when Jeff approached me about this project, he said this is going to have a lot of data. We're going to be doing millions and millions of iterations across massive portfolios. He's right. And when he first told me that, I actually didn't really believe him until I looked at the framework that he provided me. But first I wanted to start with the architecture. This is where we're at today. I actually have a more sophisticated diagram with MapReduce and Hadoop streaming and all of the Zookeeper, Uzi, all that cool stuff. But I realized two things. One is I wanted to make sure that I understood the framework correctly before I started implementing it at code level. The second part is when I started to crack open Hadoop and try to get a cluster running, I don't actually, question, show of hands, how many people here have actually tried to install a Hadoop cluster on a home network or whatever? And next question, how many have been successful at getting that up and running? Okay, that's good. Let's talk after. In the interest, I'm not a sysadmin guy, and I think that's one of the challenges of introducing these newer big data technologies. And I'll touch on that in a second again because it's worth reiterating for other reasons. So Jeff needed to see things running, working, so I said, okay, set aside the Hadoop and MapReduce for now, and let's get something up and running. So I took Python. Anaconda has a nice package of libraries to use. As we start to refine the model, I will probably be using some parallel processing packages provided by the vendor of Anaconda Continuum. Visualization, D3.js, there are already some great visualizations. I'm sure everyone here has, if you've heard of Hadoop, you've heard of D3.js. And data sources, which I want to talk about briefly. We're using Talend for big data. Talend is open source. It beats having to pay a massive license cost for developer seat for competitor products. Since this isn't independent research and development, we are on a budget. The model. Okay, so the framework here, this artifact serves two purposes. One, it actually helps me validate with Jeff that I'm actually understanding what he needs to have developed programmatically. The second part, and when we bring in the map-reduce element to this, this is a good jumping board for me when I'm designing the processes to say, okay, where do I think I am going to delineate between map and reduce? Whether this succeeds or fails, I don't know. I will let you know the outcome of that. But I think it's good to be able to visualize the model rather than crack open your IDE and just start coding away. Unless you are the one that designed the model, then that's probably a different story. But the bigger problem is organizational data readiness, I believe. So in existing business, you have legacy systems, and then you may have greenfield systems. Greenfield, exactly what it sounds like. You can go in and you are the architect. You can decide what you want that building to look like. You can define perhaps some of the building codes that you want. But with legacy, you've got to play by the rules of the legacy systems, and that's where it gets tricky with the big data. So this is really something as a data analyst that I spend a lot of my time dealing with on various projects. This isn't just at State Street, but many of my clients, and not just in finance, in the insurance sector as well, I have these same challenges. So somebody in leadership says, yes, we want to make effective use of our data assets. Go forth and do it. All right, our data assets are available. Perfect. We can deliver the system a few months down the road. Excellent. We're going to have version 2. Whatever. The reality in large organizations, in the more traditional businesses, so not your Silicon Valley type, where you do have, I believe, I'm not a Silicon Valley guy, but I do believe there is some more flexibility depending on the size of the organization. If you are in a multinational corporation with 50,000, 100,000 employees, you have a lot of people you have to talk to find out, one, where the data are, two, understand if you even have the right data, discover the data quality, and the hardest part is getting at the data. So you can't really see this at the bottom, but on the bottom of the y-axis it says, we don't want to cooperate. And this is actually a reality at getting in the data. If we're going to apply big data technologies in large organizations, you need to have, next slide. You need to have leadership support. Now I realize this is not a technical message, but it doesn't matter how superior your technology is if you can't get at the data, or even worse, if you have problems with data quality or problems with the systems that support the data quality, then that's an issue. A couple of quick examples. In one system, this was not finance, this was insurance, we had 3 different policy administration systems that we needed to integrate into a data warehouse. These systems, built in Power Builder and Visual Basic, had been running, or still are running, I think, over 15 years. 15 years. And the databases had no indexes whatsoever on the tables. No primary key indices, no foreign key constraints, hundreds of tables. Okay, so we want to do change data capture. We want even a near real time. We don't, okay, forget real time. Even if we can, in gradual bits and pieces, start to pull in changes to those databases, great. But if you don't have indexes on your tables, your stored procedures are going to bring the system to a halt. And if you have Visual Basic Power Builder applications that have hundreds, if not thousands, of connections open to the database already, these database servers are maxed out. So what are you going to do? We'll buy it an ESB, Enterprise Service Bus. We put that in, that solves all our problems. We can integrate data in real time. No, it doesn't work that way because these applications have been built in-house. Some of the developers have already retired. The source code is not documented. And I don't know how many here have heard of the online document, How to Write Unmaintainable Code. Google it. It's a great read if you haven't read it. How to Write Unmaintainable Code. I literally saw, and this actually back to a finance system, a trading system. This is not State Street, thank goodness. In the production database, but not the development database, there were two tables named Stephen 1 and Stephen 2. And we're going to put that into the big data flow and see what happens? No. We need discovery. We need leadership to say, okay, what is the problem we're trying to solve? Now, what Jeff has explained really is a salient explanation of the problem we're trying to solve. The next part is getting that support, and it's not really a technical exercise. It becomes more of a human relation exercise. So on that note, I would like to touch on the visualizations that we're doing. Yeah.
So I know we're running out. Can I get the mic down?
Let's see. Oh, sorry. Yeah.
We're running out of time here, but at the end, I think a couple of takeaways from this presentation is, first of all, the tools that have been developed in the data science arena have become very useful in finance. And I've been working in this industry for almost 20 years, specifically working on this problem, and that has not always been the case. I mean, unfortunately, a lot of the models that are developed in academia and even inside industry are not implemented because they're too hard to realize. And part of I wanted to give Nate a chance to just discuss some of the specific issues that data analysts run into, because that's something that is a real issue inside these large financial institutions, and more clients these days are asking for this kind of help. So, it's people like you, to the extent that we can get you involved, I think makes our job a lot easier in trying to result in the type of visualization we want to show. So in terms of the types of dashboards that we're producing, it's something along these lines. So we're going to show the constraints, such as the risk appetite, and then we're going to show the actual outcome of the portfolio. And then we can use some of these newer visualization tools that now are very fast and result from the use of things like latent-factor modeling, the ability to run many simulations, and then dig down into concentration risk. So what are the types of sectors that are problematic? Or what are the macroeconomic factors that tend to be driving the risk in the portfolio? And then ultimately use some of these other tools to drill into that specific source of systematic risk. So it's an interesting application of many tools that have been around for a while, and the fact that we can now use big data applications in a way that reduces, latency is a big issue. I think I have a slide in there about the talk before talked about online, nearline, and offline. We talk in terms of trader attention spans, which is about 30 seconds. So if you can't produce an outcome in 30 seconds, you might as well take 3 hours. And then you have risk analysts that will accept maybe a 4-hour latency, and then there's some processes you can run overnight. And so when you're trying to build these systems, you have to build to those particular types of performances, and it's only been recently that we can produce outcomes that really generate output fast enough to meet those types of demands. So with that, I will close, and I know we're into our lunchtime, but I'm happy to take any questions or talk to people afterward.